Okay, so the topics for this lesson, we're going to start with a little bit of discussion about speed, building off what we talked about yesterday in class, or today in class, excuse me, and the relationship between velocity and acceleration, and how to look at a graph and tell if a particle is speeding up or slowing down. And the problem we're going to look at is in your book from page 129. You may want to get that out right now, number 118. Then after we look at the speed, we're going to do a little bit more work with the chain rule. And the chain rule that we're going to be looking at involves using the trig rules. So we're going to do a little bit of the speed, chain rule, and trig. So go ahead and get your book and turn in your book to page 129, number 118, and read that problem to yourself. I'm going to sketch a basic graph of this. And you may want to sketch one in your notes also. And then my last one is about right in here. All right. We have 3 graphs, and let's see what information they give us. The figure shows the graph of the position, velocity, acceleration functions of the particle. Identify each graph. Well, we talked about position is s. The first derivative of position is velocity. The second derivative of position, which is the first derivative of velocity, is acceleration. So recall that acceleration is the rate of change of velocity, and velocity is the rate of change of position. These different derivatives all represent a different rate of change. All right. So it asks us to identify different graphs, and we know that to do that, we look at the degrees, and we identify that the S curve will be the highest degree, so this must be position. The parabola must be velocity, and the lowest power would be your acceleration, because when you take the derivative, it decreases by a degree each time. So there's position, velocity, acceleration. On your sketch, identify when the particle speeds up and when it slows down. Recall that we said if acceleration and velocity have the same sign, it's speeding up. Now that doesn't mean they're just necessarily both positive, but they're both positive or they're both negative. If acceleration and velocity have opposite signs, it's slowing down. So we have to look at the signs, speeding up, slowing down. We have to look at the signs of the value of each graph. One way we can do that is to kind of make a sign chart. Okay, so the velocity graph is going to be our parabola. It has its zeros, or its x-intercepts, let's say about 1.1, and then another x-intercept right at 4. So let's go ahead and talk about the signs of velocity, meaning where it's positive and where it's negative. So it starts at 0, and it continues. It doesn't give us a limited domain. It just says it starts at 0. Time usually starts at 0. And velocity is going to be a positive value all the way up to 1.1, so that's a positive value. From 1.1 to 4 is below the axis, so that's a negative value. From 4 till it continues is above the axis, so that's a positive value. let's look at the sign of acceleration. All right, so acceleration, it starts at 0 also, and then its y-intercept occurs about where velocity bottoms out. Notice those about correspond to the same place, or they should. My rough sketch kind of is off a little bit, but these two places should correspond, and we're going to talk about why, or discover why that would be true. Just basically, this is where a horizontal tangent will occur. If that's a horizontal tangent, that means the rate of change is 0. And remember, acceleration represents rate of change, so acceleration has to be 0 at that same location also. So there's a couple of clues to help you to analyze graphs of derivatives, which we're going to be getting more into. All right, so let's say that is about 2 3/4. So about 2 3/4. All right. So acceleration is below the axis up to its x-intercept. So those are negative values. And then it's above the x-axis from there forward. So those are positive values. Okay. So we're only concerned about where we're speeding up and slowing down. Speeding up, we look for same sign, meaning either both positive or both negative. All right, so both positive or both negative. Well, notice, take a pencil and notice that acceleration and velocity both are negative in the region from velocity's x-intercept over to acceleration's x-intercept. So if they're both negative in this region, then it is speeding up from 1.1 to 2 3/4. Then also recall that we can section off right here because that's where velocity flips over from being negative to being positive. Remember, it's negative all the way, negative all the way up to 4. So then it flips over from being a negative value to a positive value right at 4. And since it jumps over to being a positive and acceleration is positive, then the particle must be speeding up also from 4 to wherever we end up. Stop counting our time. We'll just say infinity. So that's POTS 4. Okay. The particle is slowing down when they have opposite signs. Well, they have opposite signs from 0 to 1.1 because acceleration is negative, but velocity is positive. And they have opposite signs again from where acceleration turned positive, but velocity is still negative, so that's 2 3/4 to 4. Wherever they have opposite signs, you're slowing down where those two have opposite signs. All right, another way we're going to discuss looking how to analyze these graphs, since speed is defined to be the magnitude of velocity, sometimes you may want to examine just the velocity graph and discuss where it's increasing and decreasing. So if I know this velocity graph is a parabola from here, and I know its x-intercepts about right here and at 4, and this is my velocity graph. But I want to talk about speed. I'm going to take the absolute value of velocity. So I'm going to take the absolute value of this graph means everything on the below the axis is going to pop above the axis. So speed would look like this. And you'd have to realize that this point right here corresponds to the lowest point on the graph, which we said was about 2 3/4. So notice that the particle is decreasing from here to 1.1 because velocity is decreasing in value. The magnitude is getting smaller, so it's slowing down from 0 to 1.1. Then the magnitude is getting a bigger value, so it's increasing speed. It's speeding up from 1.1 to 2 3/4. Then it slows down again from 2 3/4 to 4, and then it speeds up again. So these are two different ways to examine how a particle speeds up or slows down. One is looking at the signs on the graph, and one is just taking the velocity graph, applying the absolute value, means reflect it over the x-axis, and then discuss where it's decreasing for slowing down, increasing for speeding up. They should correspond. Okay, now let's go to your notes that I gave to you in class. And these will be your chain rule notes. And these are going to be a tad more challenging than what we did today. You're going to have to recall your rules for your trig rules and how to use the chain rule. So notice I'm asking a question, what would the inner function be? Well, I'm going to be taking the cosine of all of this. That would be my inner function. So keeping that in mind, I'm going to treat this cosine as my outer function. All right, so y equals cosine 3x squared. So the derivative is, first take the derivative of cosine, which is negative sine 3x squared. Then the derivative of the inner function, which will be 6x. So y prime will be, I like to rearrange it and put the polynomial term first. Okay, derivative, so this will be my outer function. This is my inner function. The derivative of tangent will be secant squared. Keep the function, inner function the same, then take the derivative of the inner function. So y prime will be 3 secant squared 3x. This one's a little bit more challenging. Notice it's cosine squared 3x squared. So if I rewrite it, it really says cosine 3x squared squared. Ooh, so this one's going to be a little bit more involved. Here we go. So the derivative is, this would be my outer function. So I may have to use the chain rule more than one time. So 2 cosine 3x squared to the first times the derivative that's inside. Okay, the derivative of cosine is sine, negative sine 3x squared. And now take the derivative of the argument, which would be 6x. So this derivative is going to be, rearranging terms, multiplying and simplifying, negative 12x cosine 3x squared sine 3x squared. A little more involved. Don't forget the chain rule still applies all the way through. All right. Ooh. This one we're going to have to rewrite again also. Cosine 2x to the 1/2. Here's my outer function. So the derivative is 1/2 cosine 2x negative 1/2 times, all right, my inner function derivative of cosine is negative sine 2x times the derivative of that inner function, which would be 2. So writing this in simplest form, I'm going to have negative sine 2x over cosine 2x to the 1/2 power. So your algebra is going to become really important. As we talked about today, sometimes we have derivative rules that are combined. So be careful, recognize when there's two things going on to a function. If there's a product or a quotient, you have to take the derivative with and while using the chain rule. Let's look at this example. All right, there are two functions here, 1/2 x squared and sine 2x squared. They're multiplied, so I'm going to use the product rule. All right, so here we go. I'm going to remind myself that it's the first times the derivative of the second plus second times the derivative of the first. All right, here we go. Y prime is 1/2 x squared times, ooh, I better rewrite this function up here so that it becomes evident where the inner and outer function is. This really says 1/2 x squared sine 2x squared. So it's going to be one of those long chain rule problems. All right, so now I'm going to take the derivative of the second function, 2 sine 2x. The derivative of sine is cosine, and then the derivative of 2x is 2, plus the second, sine squared 2x times the derivative of the first, which would just be x. Now I'm going to see if there's anything I can factor or simplify. Let's simplify first, because these 2's would drop out. And I'm going to bring this 2, use the commutative property, bring this 2 with this x squared. So it gives me 2x squared times sine 2x cosine 2x plus x sine 2x. And I'm going to write it as sine 2x squared so it becomes really clear that I can still factor. Notice that now sine 2x is a common term. We're going to become really comfortable with factoring as we go forward here. So sine 2x factors out. I'm left with 2x squared times cosine 2x plus, I could have taken an x out also, so I'll just go ahead and put an x out here and change that to a 1. All right, and also still factor out my sine 2x. All right, so my derivative is x sine 2x times 2x cosine 2x plus sine 2x. All right,